Okay, so hey guys, welcome to the third workshop from the DSC Research Workshop Series. Today we have Shaurya and Gaurish, NLP Basics and Advanced. He's just going to say an overview about it, and Shaurya is going to explain about the tokenizers which are being used in NLP processes. So Gaurish, let's start.
So hi guys, myself Gaurish Kumar. Here today we're going to deal with some of the basic topics related to NLP and somewhat advanced topics like dealing with the LSTM and RN models, and also talking just about an word model. So why special about NLP? So since in this current time that many things are getting popular, especially when dealing with like ChatGPT and DeepSeek, many models are coming here, and also we see the large language models that we're dealing with. So to understand all these large language models and open, we need to have a base and a good foundation on this subject called NLP. So natural language processing, this subject is basically going to deal with the text related matters. So whatever study related to like machine learning algorithms, deep learning. So these like you have come across many algorithms like random forest, linear regressions. All these algorithms may be dealing with like numerical data, or maybe have text. You may just like convert into like using or not encoding, just convert numerical data. I mean, just deal with it. But to understand the contextual like meaning, and to understand what the text tries to, if we need some models which like to understand the text and to use the meaning of the text into our models, we'll be learning about we need to know about more about NLP to deal with the text data. So basically, like we need to train a computer to a human form. So you have to understand, the computer must understand like a human how the text are related to each other. So that's why we're dealing with natural language processing. So to understand the pipeline of natural language processing, there is another like as we are seeing in many other algorithms, we need to like clean the data set before we are going to process it or going to use it for the model prediction. So same like this in NLP, we have to need to process the pre-processed data set. So basically, given a raw data like as a text format, so we need to pre-process the data, not to use this data to our model. So we have a stages of pre-processing. I'm not going to explain fully about pre-processing and all. And just to give a gist about it, pre-processing. So initially, pre-processing takes place like in the tokenization, how the words have been converted into tokens, like in the, some indices is being applied to the, each of the word or text. And this baseline pre-processing takes like tokenization, lemmaization, stemming. These are the baseline pre-processing. So if you're going for advanced, like after these texts have been converted into like some form of integers or numerical assigned to it, we need to have an like create a vector for each text. So basically, like, you need to have the understanding of, like, we need to bring the features from the given text or sentences. So we create some vectors for that. So to bring out the vectors, and we will use this vector to our models, like which are going to predictions or any other tasks that be given. So these conversion from the integers to vectors and all, we see the models related to like word embeddings, like word to vec, be having bigrams, backup words, TR5DS, and there are many like models like that. So today I'm going to talk a much little detail about so TF is term frequency and inverse dense frequency, CF and IFD. So we'll deal more about how it basically works with the TF-IFD. I'll just show how the pipeline for NLP, like we'll start with tokenization and stop over, and there are many other things in between these, like we'll go with the POs tagging in here and all. I just don't want to go through detail about it. I just given the gist about this, what happens in stemming limitation, and lastly we go with the vectorization. After these text have been converted into vectors, so we use these vectors to use in our models. Like if I'm using any models where RNN and LSTM models or BERT models. See, in case of BERT models and all, embeddings will be already done. We use there are models which will embed the text automatically, and we use this model for the embedded vectors will be used for the model predictions and all. So these are based by just about how NLP is there and how is the pipeline of it. So to talk more about TF-IFD, so I will just so what is meant by TF-IDF? So it's if you abbreviate it, it is basically called as term frequency and inverse lognit frequency. So if you before going to TF-IDF, you should know about at least just about a bag of words. So why bag of words? No, because TF-IDF is basically an improvised version of bag of words. So bag of words adds some disadvantages, so which should be like overcome by TF-IDF. So bag of words, basically what happens if you have a sentence like an example, like if I have a sentence like I love programming in Python, it just takes the number of times the given word has been occurred in sentence and just notes it. For example, it creates in a standardized in a n-dimensional vectors, and it will note the number of frequencies it has been occurred in it. But what is a disadvantage in bag of words? Like just counting the frequency of word doesn't impact the contextual meaning. For example, so words with less frequency will have a more context understanding or a more contextual meaning, and the words with higher repetition may have a less context understanding. So this does not give them a full understanding of the text, or does not impact the contextual meaning. So to give a more contextual meaning and to make an understanding of that, we will dealing with, they found a new mechanism is a model, this TF-IDF. So basically TF-IDF, we have the two terms. So this term frequency. So basically term frequency deals with if you're given any document. So if I'm telling about document, means I'm mentioning about if any sentence or it can be anything. So like if you're given a paragraph like a text, they'll be divided into each sentence, and each sentence will be IF mechanism applied. How it basically this mechanism we have made is in a formula for TF, which is TF is equals to number of times the term appears in document divided by total number of words in the document. So if for example we have a sentence like, for example, I love programming Python is a sentence. So if we want to find the TF for the word programming means, you have to know the number of times the programming word has occurred divided by total number of words in particular document. So if you have like 1, 2, 3, and 4, 5. So basically we have 5 words. Let us I write only one time. So we have an TF is 1 by 5. And another, so this basically gives a more understanding about the text. Another example I've given is, for example, if you take an understanding of today is a beautiful day, but today is a beautiful day is a normal sentence. So if you want to say the important, like which carries a more important to, so basically beauty is giving a more important to this particular sentence. So using bag of words, everything will have a count of one. Since we deal with only the frequencies, it does not give an accurate understanding or importance to particular text or not. But if you're using TF, it gives an importance, like this text is going to have some impact and gives more meaning for that. That's why TF and IF get IDF plays an important role to understand more about the context. So next, another one is IDF. So IDF is basically the log of total number of documents divided by the number of documents containing in them. So let us go with an example, like to have a theory knowledge about how it works. Let us consider 3 documents where we document 1 is related with like it is going to rain today. Document 2 will be dealing with today I'm going to going outside, and document 3 is I'm going to watch a session premiere. So now, first initially it takes the count of all the words, like takes all the unique words, and it will find the count of each word for each document. So if you see like words per document, we have going, and this is a TF which has been calculated here. So for the how this, I'll take an example of I. So I for document 1 is given 0, because if you go and see sentence, it is going to rain today because I is not even present in the sentence. So we have a 0, and 0.16 basically we got through. Here we have a formula, so it is going to rain today. So going is arrived only one time, and our total number of words basically 1, 2, 3, 4, 5, 6. So basically we have that 0.16 value for that. So it takes all the finds the TF value for all the documents. This is document 1 and document 2 and document 3, and this uses this value as TF value. So finally it also finds the IDF value. So IDF value is basically log of I2, log of total number of documents, number of documents contained in term. So if you take going and it finds all the values, ideal values for each and every verse, and finally it will create an equation. So general equation will be like multiplying TF value into ideal value for each document. So for example, going is being for, let's take a document 1 understanding. So the ideal value for going is 0, and multiply with 0.6, we will get all the zeros only. So going have an always zeros only. So how can we understand and interrupt from this table that how it is more important? So I consider, like if we see the document 1 and document 2, we will able to see that document 1 will have document 2 and document 3 will not talking about rain, but document 1 is having a value 0.17. So it means like document 1 is talking with respect to rain, and document 2 and document 3 are not talking with respect to rain. So it is away from the context of rain. And if you see another one is like the reason today, so if you see the value of today for document 1 and document 2, you have noticed that today has been array like 0.07, document 2 has a value 0.07. So basically that document 1 and document 2 are talking about present, like what's happening now. Document 3 is not talking about like present tense, so it's not talking related to what's happening now. But document 1 and document 2 are able to talk about what's happening as a present times. This was actually basic understanding of TR finders. So to have an implementation of it, like I just took an IMDb review data set from the it is a normal data set. It gives an like we have a text as an input, and we'll find whether it is an positive or negative reviews in that. So basically here I done so since tensors have been converted to what happened Python readable like data frames. Here converting everything into data frames using the reviews, and I have using NumPy, and I created a data frame where you have see the data set where you'll have a text format and you have a label format for either 0 or 1. So now I'll using the TF-IDF vectorizer. So maximum if it is 5,000, it takes an unique words, number of unique words will be 5,000. And stop words in English means like here I would like eliminated like these are the words I've been removed. I removed it. That's why stop words in English I given. And max with this I given for 5,000. So now applying the vectorizer, it gets vectorized, and I'm going to fit the transform. I'm going to fit the data into this vectorizer. So now we'll have the features of 2, as you have 20,000 reviews, we'll have a data of it, and each of 5,000 values. And next, I'm going to using these values that I got initially. How see we got the values like that. So initially, same like that, I will get a values for each of the document, each of the review like in the data set. And using this numerical value, I'll be using to predict whether it's a positive review or negative review by training the model. I'm using the basic logistic regression model. So I'm applying the X train value and Y train value, and I'm also predicting the model and all. So you can able to see the accuracy in model and all. So this is what happens in TF5. So next we'll be dealing with LSTM and RN. So before dealing with going with RN network and LSTM model, so RN is basically a traditional method. So like given a small explanation about recurrent like RN networks, I just go deep to the LSTM. So why LSTM is basically a version of RN. It's also an RN network, but it's a version of an extra or advanced version of it, because at this it's all same like that. It was able to overcome one of the problem of RN. This is like RN has a problem of like it does not carry the previous information to undergo the present task. For example, it has a problem of like vanishing gradient, they'll call as vanishing gradient, or long-term dependencies. So what's like if for example, basically Rn like looks like this only. So every time we have a single, like assume that A is in a neural network having sum of like 4 to 5 neurons, and x of t is basically the text, or each word is being given to a neural network. So basically each word will be given to the same neural network, but in a succession manner. So if you this basically goes on loop. To make it like understanding, I will take as an so it is a untold method. So here, if you see x of t is one words is being given to neural network, and h of one is output. It is going get from the output from the neural network. So what happens is basically like every time you pass a network, it just passes the sentence to its next successor. So like x of g is given to the, so you can see x of t, x of 0 is given to neural network, and h of 0 is a value, and they give the pass sentence to the next neural network, and goes on succession, but it goes within the same neural network. That's what happens. Like a loop, it goes on. That this is basically what of RNN. So what is the drawback of RNN model? For example, let's take an example of auto completion. So you have seen many scenarios like auto completion and all. Like for example, you're writing an email, it will generate and automatically, like if you want to complete the sentence, it will give an option for it to generate it. So whenever you're going to deal with auto completion and all, for example, if you're using RNN models and all, it needs to predict the last word from it. So what happens? RNN model does not carry the initial information from the text and all. So for example, I'm a scenario like I like samosa. I like samosa, and at the end of sentence, the cuisine which I chosen should be dash. If there is given means, if you, the output should be like an Indian cuisine. But what's drawback with the RN model? So it processes each word. It's like I will be processed to the RN each time. Then next a time to like each interval of time it will be given to the I, and then like will be given, samosa will be given. So what happens? RN will just does not carry the initial information, like doesn't have the process or keep the initial information. So when you're coming to the last like a last plan, it doesn't have the information, previous information to do the present task. It only carries the present information. So it does not keep an understanding about the overall text. If the document is very lengthy, it doesn't carry the initial. If the document is less and all, Rn can able to solve it. For example, the document is of size 3 minutes, the length is very size 3 minutes, it carries information since a shortage of length. We're dealing with the large document of size of very large, like sentence very large, mean doesn't carry out the previous information. So this issue is being worked on by the LSTM method. So LSTM is a very important. I like to explain about it. So LSTM is one of the most current and advanced method. So it's like LSTM is long short term memory network. So why what happens within this is basically LSTM is also an RNN, but it has an extra state called cell state. So what a cell state carries, basically it carries the prior information of the prior input data. For example, tan is a function which is used in LSTM RNN. So dealing with, I will just explain that. So this line, if you're seeing, no, this line is basically one of the cell state. So this cell state will not be visible in the RNN. So this additional thing is being given in the LSTM. So what happens is whenever you're getting like x of t minus as a prior text, so it carries the information from the prior neural network, and also it uses it. And at each time it will also has a criteria to whether forget the text or forget the information or add a new information. So this new technique is only present in LSTM, where can able to forget or add a new information at every time when a word is being given to an LSTM or not. So it has three gates where you can understand more detail about it. This is the RNN neural network which has been seen, I told you. So LSTM, as I told, that this is known as a cell state. So previously I told about what is my cell state and also what are the functions here. So compared to RNN, how it works basically about, we have a cell state called C. So CT minus one is the information obtained from the left, like prior text, and it will be having a three gates. So this one is the forgot gate, and another one is an input gate, and another one is the output gate. So these three gates plays an input role. Forgot, what does the meaning of forgot gate is basically it uses sigmoid function and uses the weight of x of t. I'll just explain. So if you're able to see, you'll have more understanding about it. So here, sigmoid function is used here. So basically, it calculates the weight of the x of t, is the input you're given, and h of t is output from the previous text, and it will calculate the weight of it, and the sigmoid function is applied to the weight of both of it and the bias of it, will get an output. Say sigmoid function will have an output either between 0 or 1. So if the output is 0 means it will completely ignore the information. If the output is basically 1 means it will add an information, or it will keep the information alive. So because maybe the information is needed for the processing or next level. So if it's 0 means it will disregard the information about it. That's what it is the most important thing within an LSTM network. And next one is about the input gate. So basically, what happens if you need an add and a new information to the cell state to carry it towards the network, we'll deal with about the input gate. So input gate, you have two functions, one is sigmoid function, tan x function. So sigmoid function is applied to the weight of h of t minus 1 x of t, which is the previous output, and x of t. And c of t is another where tan x will be applied to it, to the weight of the h of t minus x of t. So this values obtained will be multiplied and will be given to the input gate. So the new information, like either the value can be updated or it can be decided by the C of t, where C of t represents new information, I of t represents the updated value. So it can be multiplied and will get the passes to the input gate. So you can see the C of t is basically f of t into C of t minus 1 plus I on t. So it also takes the value from here, combines with the value from input gate, and both either C of t minus 1, either we don't have any value from this. Like if it is sigmoid function equals to 0 means it disregards all the information and we have only new information. If the sigmoid function is 1 means we'll be combining information from the previous as well as the current information. And output gate is basically a simple Lagrange function that is obtained from the cell state and sigmoid function, and thus and the output is obtained from the sigmoid, and the cell state will be multiplied and will be given as h of t, which will act as h of t minus 1 for the next neural network. So you're able to see the complete diagram of C of t minus 1 cell state is being converted here and goes through the value. So this is basically what LSTM works, and h of t minus 1 and x of t. So I'll give a more detailed information by using a text manner. So for example, understand like the wall eats samosa almost every day. It should be hard to guess this. Fair questions Indian should be it. So what happens, this LSTM will carry the information. For example, the word eats and all doesn't have an a priori like importance and all. It also takes as if it all input gate. It only adds only it as an important value by using the functions and all. So for example, samosa is there, so it adds the value and carries the value till the end of the word. And when it comes for the last word, gives a value of Indian. That's what happens in LSTM network. But in case of RNN, it doesn't carry. Like for example, it may carry at first initial network, it may carry the wall and the wall eats and samosa, and it goes with almost every day. So it skips the samosa and doesn't carry the prior information at all. So I'll see you can able to see the more description on how it happens. Like as I told about the friend gate, how it works, the sigmoid function for the h of t minus 1, x of t is obtained from here, and both will combine to get an forget gate. So it will multiply, we'll get the forget gate, and this information either can be added or removed. It depends upon the value we obtain from the sigmoid function. So this also when x of t is faster way gaining, so faster we apply go through this gate forget sigmoid function, and it also it will be worked with the sigmoid function or the weight of h of t minus 1 and the pasta. So either pasta, because pasta has more information and has more importance, so it will add it to the input gate is adding memory of pasta, so it gets added to it, and we'll get an C of t and h of t is after from the output gate over. So now I'll explain how it model like so basically now I took in the same IMDb review, so I'm going to use how the LSTM network has been built. So basically I used all the import all the models for the LSTM network. So LSTM has been imported and dense and dropout layers have been imported. So next I just tokenize normally, like using tokenize function, I just tokenize all the words into some integers will be assigned to each of the text which is given to it, and then we use it. And when we feed the tokenizer into data, and then we convert into sequences. So after converting a sequence, we are doing a padded sequence. For example, what happens in padding, like if you have a sentence of 3 words, like 1, 3, 5, but you have a size of 5,000, means like it will give a 0 for remaining size of the vector. So if you're having n vector, like, and if having the number of length is basically less than n, means the remaining will be covered with zeros. So we have two types of padding. I don't want to go deep with it. It's like post padding or pre padding. Zeros may be added before or after of it. So once padding is done for each sequence, I'm dividing the data set into X train and Y train. So here I'll be creating the model for the LSTM model, where I'm going to input dimension will be 5,000, the features will be maximum 5,000 can able to see here, and output dimension each word will be given assigned to a dimension vector of 64 and 64 dimension vector, and maximum input length is 100. You can see here. So maximum 100 unique words can be assigned to it. So I add a model of LSTM with the 64 is given. Each text will be represented as an n dimensional 64 dimension vector, and activation sigmoid function is added here, and basically like this two layers have been added here, and I'm just compiling. Since I'm dealing only with positive and negative, I'm using last function's binary cost entropy, and then you can able to see the summary of each of it. So now I'm able to train the fit the model to the given data set and just train it, and you can able to see the accuracy of the score. So this is a basic understanding how LSTM and RN works. So now going on with BERT model. So what happens in BERT? So explaining about BERT is not like what is the most currently used word is method is basically BERT. So if you go and say Google and all, if you go and type search, it automatically request, like it'll give you some request like ideas and all. So it's basically Google is using like BERT model from 2018. So what's most about BERT model is like if you have an like each text will have a set of features for it. So to compare the features and to make it more unique from other text and all, BERT model used. So for example, let's take the embedding method is the word to vec. So word to vec is basically if you given text and all, it will create and some n-dimensional vector representing the word. So what is the problem with the word to vec is, for example, there are words which may have a different meaning with respect to different sentences. So that time it doesn't happen to word vec. Word vec will give the same dimension vector, same features for the same for different sentence. But though the word is having a different meaning or context. So for example, let's take the word fair. So fair can have two meanings. Either can be an fair play, or we're dealing with like the fair conducted in different colleges and all. So it has two different meanings. Like it depends upon the it tells about how the game is played, and tells about the event that's happened in other places and all. So if you use word to work will represent the same vector representing the fair in both sentences. But what happens in bird will has an idea. Bird gives an contextual embedding. So with reference to the context, bird will have different type of features with a sentence. So that's why the most important thing BERT model. So BERT model plays an important role with giving a contextual features for each of the word in the sentence. So that's why it making it more unique when compared to other models, BERT model. So BERT, what happens is like BERT not only gives a feature like vector for each text and all, it also gives a feature vector for overall sentence. If you given a sentence, it creates some it gives an n dimension or some size of vector for one particular sentence. So that also has a capability from BERT. So mechanism of like I'm not going to deal with more like predictions or text classification with BERT. I'm going to explain how embeddings have been happening in BERT model. So I import like herb model and text has been imported in Word. And next time dealing, I just import this pre-process. Like if you go for the TensorFlow website and if you go and search Word, you will have an separate like encoding method and you have a pre-processing. So it along with the encoding, if you take any encoding model, it will have a corresponding pre-processing. So if you go and search for that, it will have that corresponding pre-processing encoding done. So I'm creating a hub layer for that. After creating a hub layer, this model can act as a pre-processing model. So you can apply this pre-processing model to for terms. For example, it has have a sentence like nice movie indeed, and I love data science club. So you apply the model which is being created here. It just gives an three value. It is like dictionary. So it will create a dictionary where all the way pre-processed or not. So input mask, input word IDs, and input type IDs. So what input mask is telling is about, so it gives a size of 128 vectors, and each five, so you have a size of 5 ones. So basically a nice movie indeed represents 3 words, length of 3. But why it is having 5 is basically initially first one is CLS, and last to be considered as SEP token. So the remaining 3 represents the nice and movie indeed the words. These are considered as this will be marked as a one. And comparing to the I love science syllabus, like we have a same like I love data science club. So we have the 5 words, and the remaining actors and SEP and as well as the CLS token. So this tells about mask will tell about a number of what are words present in it. And input type ID is basically we know the it doesn't need about input type ID because we're not dealing with since single sentence we're dealing, we don't need about type IDs. Type IDs will play important when we go on with multiple sentences we have text. Say, for example, having a multiple text and all like sentences in the single text, then we can use you don't find you'll have some difference, but you don't find difference since we're dealing on the single sentences. And third one is about input word ID is a unique ID given to each word in a sentence. So for example, love movie didn't is for the love is given some token 335. But what's the thing we can observe is basically 101 and 102 will be same to same for whatever sentence it is because it stands for CLS and 102 stands for the SEP token. So both will be present for if you see for second author it becomes same 101 and 102. So it will be remaining same and constant for all type of sentence you give. And next, I'm going to create an encoding. So, and since encoding URL is the one that I used here, so the same URL I'm applying to here as layer. And then I'm creating this model to the text preprocessor. Once the process preprocessed text is being done, I'm using the text to the embedded model. So this embedded model basically gives an output as a dictionary, where it has a pool output, a sequence output, and encode outputs. So what happened? What is basically about pool outputs? So sequence output is basically if you go and deal with pool output, they deal with the pool output will give the embeddings of the each of the text. Basically, have a size of 768. So for each sentence, will given a size of 768. So why is 768? 768 is a fixed size for each sentence. For example, I'm giving ILO or data science club. It gives word embeddings for each of the sentences, like from 768 size, and we have that pool output, and then we have a sequence output. So sequence output is basically sequence output is basically we see sequence. What is meant by sequence output is basically we have it will give a word embeddings for each of the every word. So basically pool output is it gives an embedding for the each sentence, but sequence output will give the each for each word present in the sentence. It will give the output. It will give the word embedding. So you're able to see the 0.7, so you have a set of values up to 768. So what is my encode? So length of encode output. So dealing with encoder, now I'm dealing only with the bird. There are two types of ones: bird small and bird large. So bird small will have since bird is basically transformers, it will have an 12 encoder layers inside it. If I'm dealing with the bird small model, that's why it gives a length of the encoder output is 12. So what happened since the bird model is around 12 encoder level, each encoder level will give an output of you can see the output generated by here. So we can be able to see that each layer will have 12 layers. So each layer will give an output of shape of 2, 1, 2, 8, 1, 6. So it gives an The overall length of 768 is n dimension, and 128 is for each word. So basically, each particular encoder layer will give the output for each sentence, like, and each word will be given an output of embeddings. That's why you're able to see that output is going to be very big because it gives 12 values, and each value will represent the word embeddings for each word in each sentences. That's why given encode outputs. So that's all from my side. I'm able to.
Yeah, thank you, Gaurish. The workshop was very well conducted, and you also showed the course and all, even with the diagram. So I thought, I mean, I believe it's very good.